Continuing on, section 9.4. Now we're going to do objective 2 with the rational inequalities. So we first looked at quadratic and now we're looking at rational. So rational expressions, we've worked with some, and any polynomial over another polynomial is a rational function. So they can be really simple or they can be a lot more complicated. So anytime you have a polynomial over another polynomial, that's called a rational function. So these are similar to solving the quadratic inequalities with one little catch. So let's go through that. So here again, we're trying to get a visual picture of what's going on. So here is a graph of rational function. And I want to be looking at the graph to figure out when are the y values positive. So remember again, the x-axis is the dividing line between y values that are positive or bigger than 0 and y values that are negative or smaller than 0. So if I'm asking where are the y coordinates bigger than 0, then I want to know which pieces of the graph are above the x-axis here. So looking from left to right, I can see that from x is negative infinity up to -1, I definitely have positive values of the function. But then it's negative up until this x-intercept, when it starts becoming positive again. So union with from 1 to 2, but then I have a vertical asymptote, so that x value can't be included, but I do want this piece from 1 to 2, and then union from 3 to infinity, because from 2 to 3 the graph is below the axis. So this is the solution interval notation. But then we also need to show this on a graph, number line, a graph of the solution set of x values that make the inequality true. Okay, so then the B part is where are all the parts of the graph where the y values are negative. So for B, we're looking at, let's see, from -1 it is definitely less than 0 there, and it can't equal -1 because we have a vertical asymptote there, and it's negative all the way up to +1, and then it equals 0 at +1. So we need to put the square bracket there. Then this is union with, it gets negative again at the vertical asymptote of 2 and stays negative until 3, and then it's equal 0 there. So check and make sure that every x value that's represented on the graph is included either in part A or part B, and that vertical asymptotes are not included. So that's just a good way to check your work. So then we know from -1 to 1, we want that piece of the number line, and from 2 to 3, we want that piece of the number line. Okay, so when we're doing it algebraically, you have to get a 0 on one side. Not optional. There is no other way to solve it. You cannot multiply both sides of this inequality by the denominator because you don't know if it's positive or negative, and it's an inequality. So if it was negative and you multiplied both sides by it, the direction of the inequality would have to reverse. So never, ever, ever multiply an inequality by something that has an x in it. So instead, you have to put the 1 on the same side with the rational function, get them over a common denominator, and then we'll go from there. So we're going to have x plus 4 minus 2x minus 4 over 2x plus 4. So that looks like negative x over 2x plus 4. We want to know when is that greater than or equal to 0. So negative x over 2x plus 4, when is that greater than or equal to 0? So then you need to find zeros of the graph, which is x-intercepts, which is when is the numerator 0. So that's x equals 0 for this example. And then you have to find numbers where the function is undefined. So that's going to be where is the denominator 0. And that happens when x is negative 2. So those are the two dividers that divide the number line into the pieces that we need. So negative 2 and 0. So notice that x can never actually equal negative 2, so you'll never have negative 2 be included in your interval, but x equals 0 can be included. So again, we have 3 intervals, so I'm going to make my chart, and this chart is going to be useful in a lot of different ways, and so it would be really good if you got used to organizing your information this way. So we have negative infinity to negative 2, not including the negative 2. So I'm going to use a test point of negative 10 and say you can either go to the original inequality or your rearranged one, because they should be equivalent if you did the math work right. So it looks like I have positive 10 over a negative number, and really that's all I care about is it positive or negative? So the question is this positive? And the answer is no, because if I take a positive number divided by a negative, it will be negative. So I don't want this piece of the number line. So then negative 2 to 0, 0 will be included in the interval, but I can't use it as a test point because it's an end point of the interval. So let's use negative 1. So I'll have the opposite of negative 1 over 2 times negative 1 plus 4. Well, now I have positive 1 over positive 2, and that is greater than or equal to 0. So I know I want this piece of the number line. And then, of course, we'll do 0 to infinity and test 10. So I'll have the opposite of 10 over 2 times 10 plus 4. So that's a negative number over a positive number. That's definitely not positive. So I don't want this piece. So my number line answer is x can't be negative 2 because that's going to be a vertical asymptote, but it can be 0 because look at the original inequality and 0 works just fine. And then you can see that the interval notation just follows right from the graph. Okay, so here's another example. I want you to try it and then come back and see how you did. So I want zeros of the numerator, and there's just one, x equals negative 5, and zeros of the denominator. Well, now we're going to have 2, x equals plus or minus 2. So we're going to have 4 intervals. We're going to have negative 2, 2, and 5 as the dividers. So our intervals, the first one will be negative infinity to negative 2. So let's use a test point of negative 10. And then negative 10 plus 5 quantity squared over negative 10 squared minus 4. We want to know if that's positive. Well, the numerator is always going to be positive because it's a squared quantity. And then here, 100 minus 4, that's going to be positive. So it's true that the ratio is positive when we're in this interval from -infinity to -2. And we can't include -2 because it would make the denominator 0. So then we have -2 to 2, and 0, of course, easy one to test. So then I'm going to have some positive number, and it really doesn't matter which, I just need to know positive or negative. But then I have 0 minus 4 in the denominator, which is negative. So this is not true, so I do not want this piece of the number line. So then 2 to 5, let's use 4. So I'm going to have a positive numerator over a positive denominator. So this is true, and I want this section of the number line, but I don't want 2 because that would make the denominator 0, but I do want 5 because that just makes the numerator 0, which is fine. That gives me my e equals 0. Then 5 to infinity, let's test 10. And I have a positive numerator over 10 squared minus 4, which is also positive. So I also want this piece of the number line. So I should go back and erase this square bracket because the interval continues. So it goes right. This is not correct. So this is a dud. Darn it. That's what happens when I do it later in the day when I'm not fresh.